All right, so we are continuing to talk about similar triangles. Okay, so we have a couple theorems to learn today. The most important is called the side-splitting theorem. Now, you may not have heard of the saying, like when somebody tells a funny joke, they say, "Oh, that split my sides. It was so funny. Like I was laughing so hard." I know nobody's heard of that saying, but whenever I hear about side-splitting theorem, I always think it's kind of a funny name because of the side-splitting. Well, anyway, so I put a joke on the top of these notes because it reminded me of, side-splitting jokes. I named my dog 5 Miles, so I can tell everyone I walk 5 miles every day. I get it, right? I think it's a good idea, actually. Okay, but seriously, the theorem is called the side-splitter theorem or the side-splitting theorem. And it is used when you have a diagram that looks like this. Now, we have seen diagrams that look like this before. And we have handled them because we know that they are similar triangles. So we're able to handle them as similar triangles. All right, so we're talking about side-splitting theorem, but we were saying that this diagram is a diagram we've seen before. So you don't have to write this on your notes, but I just want you to think about how we've done this type of a problem before. If I give you something that looks like this, I actually have given you something that looks like this before, and I say that this is 3, and this is 5, and this is x, and this is 8. How would we solve for x? Well, we always have to, and I would have to be told that these are parallel. Since these are parallel, we know this and this are corresponding angles, this and this are corresponding angles. Therefore, these two triangles, large and small, are similar to each other. So we can set up a proportion using the sides of the triangles. Now, we have to be careful because we have this smaller triangle, D, A, E, and we have the larger triangle. And they're overlapping, so it's always a good idea to draw them separately and label the sides carefully. Now, in DAE, I have this side is 3 and this side is x. I don't really care about the other side. I'm looking just for x. In the bigger triangle, what's the length of AB? 8, right? Because it's 3 from here to here, and then another 5, and that makes it 8. So you have to, when you label the overlapping triangles, label them carefully. So we did 3 plus 5 to get 8. What would be the length of AC? Okay, big difference, right? It's not 8x. That would mean 8 times x. That would be like if we did 3 times 5 and got 15 for that side. We wouldn't do that. 3 plus 5. So over here we have to do x plus 8. Okay, so Charlie, pick up the notes and then see if there's anything else there for you. Okay, so when we do the proportion, we're going to say 3 is to 8, left is to left, as what? X is to x plus 8. Does that make sense? Yes? Okay, so now when we cross multiply, like we know how to do with proportions, we're going to get 8x equals 3 times parentheses x plus 8. And that's 8x plus equals 3x plus 24. And we get, subtract 3x from both sides, 5x equals 24. X equals 4.8. So x would be 4.8. This is familiar to us, yes? Okay. So what do we need the side-splitting theorem for? Well, the side-splitter theorem says if lines are parallel, which they are in this case, and the example we just did, then the sides are split proportionally. This is a big difference with what we write as our proportion. What it's saying is that this top is to this bottom as this top is to this bottom. They're proportional. They're split proportionally. So in the example that we just did, instead of doing it with similar triangles, we could do it with side splitter. Again, you don't have to write this down, just watch. So with the side splitter theorem, we would say 3 is to 5 as x is to 8. Isn't that so much simpler looking? There's no distributive property. We don't have to worry about the x plus 8 on the side. Doesn't seem like it would come out the same, but sure enough it does. 3 times 8 is 24. 5 times x is 5x. X is 4.8. See what I said? Yeah. Okay, so that's what this theorem says. It's like a shortcut. It's like you don't have to worry about drawing them separately and setting them up like we did before because the sides are split proportionally. So that said, let's do these practices. The first one. How would we set up our proportion? And by the way, this is a plus sign. I know it looks like a minus maybe on yours, but it's actually a plus sign. So how would we set up this proportion? What over what? So 12 over x plus 1 equals 9 over x. Top over bottom equals top over bottom. Don't forget to distribute. Solve for x. We get x is 3. Okay, you guys try b on your own. Okay, so for this one, you should have set it up as a over a plus 4 equals 12 over 18. Cross multiply and solve, and you get a is 8. By the way, since this is set up proportionally, you could take parts and wholes as long as you're on either side, as long as you're taking the same parts and wholes. In other words, I could have done like 12, top is to whole as top is to whole. Or bottom is to whole as bottom is to whole. I could have done bottom is to top as bottom is to top. Any combination that kind of is the same thing that you're taking on both sides will work. Okay, so there's a corollary to this theorem if you look at the other side. And it basically is a little bit more general. Side splitter is specific to triangles. This kind of generalizes. If you actually have lots of parallel lines, not even forming triangles necessarily, that are cut by transversals, let's make one that's really slanty like that, okay? Then if all of these lines are parallel, all of these lines are parallel, then that means all of these parts that the parallel lines are cutting the transversal into, they're all cut proportionally. In other words, if I name this distance from here to here, I'm going to name it A, B, C, D, E, F, G, H. Okay, like I got a whole bunch of things here, but know that this A stands for the distance there, and E is the distance there, etc. Okay, so when you have this situation, you can make proportions out of any of these parts. I could say A is to D as, what would I have on the other side? So on the other side it would be E is to H, correct. Does that make sense? I could do C is to D as G is to H. All right, let's take another one. I could do A plus B is to D as, right? Okay, I could do one more. D plus B is to A as, you see that? Okay, so you could do any combinations. You could do the whole side is to A as the whole other side is to E. Any of those combinations will work because they're all split proportionally by the parallel lines. That make sense? Okay, that's basically what that corollary says. So now to solve a problem, this is a clipped out of the book here. 3 campsites are shown in the diagram. What is the length of site A? So we're trying to find the length of this along the river based on the fact that all of those lines are parallel, and we know the length of the sides on the other side of the site. So if I call this x, what am I going to do? X is to what? Okay, this is actually an 8. It's the same on your paper. X is to 8 as 9 is to 7.2. Does everybody see how that relates? So you can cross multiply and solve. 7.2x equals 72. What's x going to be? X going to be 10. Yep. So 10 what yards? Okay, there's one more theorem, and this is, actually, before I do that theorem, I need to, sorry, I skipped this part down here. We got to go back to the front. This is like the most important part of this lesson, and I almost skipped it. That was not a good idea. We learned side splitter. It makes a lot of sense, makes things a little easier, kind of a shortcut, but it doesn't always work. Oh, come on. So it's a very specific situation where it works, and it only works when you have information on your triangle about the two sides that are split. In other words, in this example, MP is split into MK and KP. And we have a length for MK and a length for KP. MN on the other side is split into ML and LN by this parallel line. And we have information on the side 9 and x. That's when it works. This is when it doesn't work. You cannot use side splitter. Same looking diagram, but what's different here? Yeah, they didn't label this other side. What did they label? The parallel sides. Is 12 and 30 split parts? No. They are whole sides, and they're both whole sides. This is when you cannot use side splitter. So when they give you the information labeled on the parallel sides, you have to go back to doing this the old way. We have to do this way. Okay? So the base of the little one is 12, the base of the bigger one is 30. The left side of the little one is A. Well, the little one is just A. right? What is the side, the whole side of the bigger triangle? A plus A plus 4, right? Because it's this part, A, plus this part, A plus 4. So A plus 4 equals 2A plus 4. So this side is 2A plus 4. And then we would set up a proportion from there. A is to 2A plus 4, as 12 is to 30. Don't forget to distribute when you solve. Try part B on your own. Remember to draw them separately because these two are not talking about the two split sides. You're talking about one of the split sides and then the whole parallel side. So we have to do this as similar triangles, not as side splitter. Okay, so just to make sure we're on the right track, this is 10, and this is x plus 2 on the small triangle. On the big triangle, the whole side would be x plus 10, and the bottom is x plus 14. So when we set up our proportion, we have 10 over x plus 10 equals x plus 2 over x plus 14. Cross multiply, we're going to get 10 times x plus 14, don't forget parentheses, equals x plus 10 times x plus 2. Yes, we have to distribute everything here. FOIL if you think of it that way. X squared plus 2x plus 10x plus 20 equals 10x plus 140. We've got combined like terms here, but we still have a situation where there's an x squared term and there's an x term. So we have to factor. So get everything equal to 0 on this side. Subtract 10x, subtract 140. You get x squared plus 2x minus 120 equals 0. And then we have to factor that. We're thinking what multiplies to be 120, negative 120, and adds to be a positive 2. We do not need a box. We do not need a split method. We just, yep. So good. X and X, because there's no number in front, nothing tricky. And then 12 and 10. And for it to be a positive 2, it's going to be a positive 12 minus 10. Good. So x equals a positive 10 or negative 12. Now, since this is not just a simple factoring question, this is a geometry question, we have to make sure that those x's don't create something impossible in our diagram. If I plug in negative 12 as x, is that okay in this diagram? No. Can I have a length that's negative 12? No, so I have to cross out negative 12 as an answer. And x is just 10, would be the only answer that makes all of these segment lengths positive. Negative 12 makes them negative. Okay, any questions? All right, so this last theorem is called the triangle angle bisector theorem. We learned about what an angle bisector is in a triangle like a while ago. Basically, any angle that gets cut into two congruent pieces, we could call that thing cutting it an angle bisector. It's cutting the angle in half. Well, what this theorem says is that when that happens, it cuts through that opposite side, usually unevenly. In other words, CD is a little bit longer than DB, right? Can you kind of see that?
Yeah.
The reason CD is a little bit longer than DB is because side AC is longer than side AB. This is kind of a crooked triangle, right? So when you do the angle bisector, yeah, the angle gets cut in half, but you go through that other side, the other side doesn't get cut in half. It gets cut unevenly because we have a really long side. Let's say we had a really short side. Cut this, right? You can see how if it's a long side, then that segment across from it is a little bit long as well. So somebody figured out, I don't know who it was, but somebody figured out that these sides and parts of the opposite side are proportional. CD is to AC as DB is to AB, and every combination of that. Now, I have a little trick for this one. If it's an angle bisector of a triangle, if you can locate that angle bisector and confirm that these two are the same, right, then you can just put an equal sign right on that angle bisector. Because visually, that diagram is showing you exactly how to set up your proportion. 10 over 12, 18 over x. So do you see how that equal sign, if you draw that equal sign right on the angle bisector, you might have to turn your paper if it's, facing the other direction, but if you draw it right on the angle bisector so that bisector is going right through your equal sign, and then just create the proportion based on where the numbers are. 10x equals 12 times 18, which is 108. No, it can't be 108. It can't. 216. I had already divided. The reason I got 108 is I simplified on my paper. I simplified 10 over 12. Remember, anytime you have a fraction, you can simplify it. So 10 over 12, I could make 5 over 6. So that's how I got my 108. I did 5x equals 6 times 18, which is 108. So divide both sides by 5, and x equals 21.6. Yep, you can have 10x equals 216, and then divide by 10, and you get 21.6. Okay, you guys set up B on your own. Draw the little equal sign. Write your proportion. All right, so this one should be y over 9.6 equals 24 over 16. 16y equals, oh, I simplified it again. I made this 3 over 2. You can do that, right? So then you have 2y equals 28.8. And so y equals 14.4. All right, this homework assignment that's written right here is actually your homework assignment. Okay?